And we have last presentation by Levi Lustrom, who will continue the same area of research, the photoinduced charge transfer at the interface of inorganic and organic materials, with some specifics and some interesting analysis.
Okay. Thank you all for sticking around. Today I'm going to talk about two different dyes and the rate at which holes will be taken from the quantum dot. So the motivation behind my talk is we want to put it inside of a solar cell, and there's several things that need to occur, but the things that I'm interested in are the rates at which the electron is taken from the quantum dot in the hole. And we want the whole rate to be faster than the electron because that helps the system be more efficient. So to do that, we want to try and find ligands that will extract the hole from the quantum dot. And there was a paper by the Weiss's group where they took the same acceptor and they linked it through two different linkage groups, one being PTC and one being BA, and I'll just say the first one, not the entire one, the entire name. And PTC has been shown to very well interact and couple with the quantum dot, and it makes the absorption spectra redshift, and you can kind of think of that as the particle in a box. The box has got slightly bigger because it interacts with the sulfur on the group.
And again, what's the difference between your linkage just because so small? Picture?
Oh, sorry. So it's sulfur for PTC and oxygen for DMA. So
it's carboxylate and the
yes.
group.
Yeah, so that's the only thing that's different, is the oxygen and sulfur. So this is my system. I have it totally neutral, so I have 33 cadmium selenium quantum dot, and then I have my full ligand with an extra cadmium, and then I took a reduced model of the ligand to keep it charge neutral, because these systems typically are charge neutral, and we don't want the charges to close the band gap. So the methodology, just like everyone else, I use VASP with GGA, functional PBE, and my main tool in this is when we collapse the COMCHAM orbitals into either one dimension or just, two dimensions. So we have Z and then the amplitude, or just the center of mass. And that's given by these equations. So in the experiment, they excite at 2.95 electron volts. And if we look at the states that are important around that region, we can already see the difference, where for the PTC, we have some states that are very charge transfer in nature, which would mean that we already broke our exciton into the electron and hole, so then the hole can be extracted very easily. But for the BA, none of the states are that charge transfer. And how we get this is if we look at our, this is the different states, and then plot the center of mass, and we can see here that there's, it's localized on the ligand, and then everywhere else on top is localized on the quantum dot. And we can see that a lot of the PTC are excited, the hole is in this region. So the BA has to relax down to almost a HOMO level to be able to get a charge transfer state. So this is very important because we want to see charge transfer. So from this diagram, we can make a conclusion that PTC facilitates charge transfer because it's either initially excited to a charge transfer state, or it has very few states to relax to get to a charge transfer state, where BA, it has to relax almost to the HOMO level. So then this is just a partial charge density of the highest charge transfer state. So this is 353, and we can see that the charge transfer is only on the ligand, and there's no localization of the hole on the quantum dot. So in conclusion, we can conclude that PTC facilitates charge transfer because it is either initially excited to a charge transfer state or it is very close to a charge transfer state, where BA has to relax down to a charge transfer state, which will increase our rate for hole extraction.
Okay, let's thank Levi for